Now, next topic, that is Coulomb's law. So, with the help of large number of experimental observations related to the forces between charged spheres, scientist Coulomb represented the law which represents the force acting between two point-like charges. So, he suggested this thing, the force, the electric force, it is also known as Coulombian force. The electric force between two point-like charges directly proportional to the product of these charges and inversely proportional to the square of distance between those two charges. And this force is along the line joining to those charges. Okay. Now, suppose as shown in the figure, we have two charges Q1 and Q2 which are separated by distance R. Both the charges are taken here, positive charges. Okay. If one is positive, another one is negative, then also here we have to take the magnitude of charges, right? So, at present, if we think about the magnitude of the force, then we have to take the magnitude of Q1 into Q2. Now see, if we have two charges Q1 and Q2 and the separation between these two charges, that is R, then the electric force between these two charges, F, that directly proportional to the product of these charges means Q1 into Q2. And it inversely proportional to the square of distance between those two charges. So we can write F proportional to 1 upon R square. So resultantly we can write F proportional to Q1 Q2 upon R square. Here the proportionality constant we can introduce, that is K. So resultantly we can write F equal to K Q1 Q2 upon R square, where value of K, that is 9 into 10 raised to 9 Newton meter square per Coulomb square. K, that is equal to 1 upon 4 pi epsilon 0, where epsilon 0, that is the permittivity of a free space. And if we make epsilon 0 as a subject, then we can write 1 upon 4 pi k. If we substitute here value of pi and k, then we will get permittivity of a free space, that is 8.85 into 10 raised to minus 12 Coulomb square per Newton meter square. Permittivity of any medium, that is nothing but the measure of the response of that particular medium to the electric field. So we can write the Coulomb's law in equation form as F equal to 1 upon 4 pi epsilon 0 Q1 Q2 upon R square. Okay. Now, with the help of this particular equation, one can give the definition of 1 Coulomb amount of charge also. How? Suppose we take the charges Q1 and Q2, both are equal and that is equal to 1 Coulomb and are separated by 1 meter. Then F will be equal to K, that is 9 into 10 raised to 9 Newton. So from this one we can say this thing, if two identical charges or two charges with equal magnitude are separated by 1 meter and if the force between them is 9 into 10 raised to 9 Newton, then charge on each one, that is 1 coulomb, or we can say each charge that is of 1 coulomb. Clear? Now, say if charge Q1 and Q2, these two are in some medium, means between these two, if some medium is there, then see if medium is not there, free space is there, then here the permittivity of a free space appears. But if medium is there between two charges, then very simple, we have to introduce here permittivity of that particular medium. So we can write the force between those two charges separated by distance r in any medium, that we can write 1 upon 4 pi epsilon q1 q2 upon r square, where epsilon, that is permittivity of that medium. Now epsilon upon epsilon 0, that is the relative permittivity of the medium, means permittivity of the medium with respect to that of permittivity of a free space. So that is relative permittivity. It is denoted by epsilon r. It is also known as dielectric constant of the medium. So from this one we can write epsilon, that is epsilon 0 k. So here if we introduce epsilon, that is epsilon 0 k, then we can write Fm equal to 1 upon 4 pi epsilon 0 k q1 q2 upon r square. But 1 upon 4 pi epsilon 0 q1 q2 upon r square, that is F, this one, means Fm, that is F by k. It implies that if between two charges the medium is there, which one is with dielectric constant k, then electric force between those two charges becomes 1 upon k times then the initial one. Now, this equation that you have to remember, that is important for entrance examination. See, between these two charges, entire space is not filled with the medium, but small part is filled with the medium. It implies that between these two, the medium introduced, that is with thickness T, where T is less than R. એટલે થોડાક પાર્ટમાં medium છે અને પછી થોડોક part free space છે. અને medium જે introduce કર્યું એની thickness T છે, where T that is less than R. So in that particular case, we can write the equation of force, that is 1 upon 4 pi epsilon 0 q1 q2 upon r minus t plus t root k whole square, right? This equation is important for entrance examination. You have to remember it. That is not in your text, okay? So this one is Coulomb's law. Clear to all of you? Now, Coulomb's law in vector form. So, here to represent Coulomb's law in the vector form, consider the Cartesian coordinate system. Now, with respect to the origin, suppose the position vector of charge q1 is r1 and position vector of charge q2 is r2. Okay. Now, position of 1 with respect to 2, that is represented by vector 2 to 1, that is r12, position of 1 with respect to 2, that is r1 minus r2. Now, here q1 q2 is greater than 0, means both the charges are positive, so force between these two, that is repulsive. So force on 1 by 2, so 2 repel 1, so that will be in the direction as shown in this figure, here in this direction. And force on 2 by 1, so that is also repulsive 1 repel 2, so that will be in this particular direction as shown in the figure. Now, suppose first we think about force on q1 by q2. So force on Q1 by Q2, that will be in the direction from Q2 to Q1 because that is the repulsive force. So Q2 to Q1, this direction. Now force on 1 by 2, that is K Q1 Q2 upon R12 square. Now to give it vector notation, we have to multiply it by unit vector which is in the direction of the force. Suppose in this direction of the force, the unit vector is R12 caret. Then we can write the vector force F12 that is equal to K Q1 Q2 upon R12 square into R12 caret. Where R12 caret, unit vector, that is vector upon its magnitude. So vector that is R12 upon its magnitude R12. So we can write vector R12 upon R12 simply. Now if this unit vector is replaced by vector R12 upon R12, then we can write this in denominator R12 into R12 square, that is R12 cube. But this is the magnitude of R1 minus R2. And this R12, that is vector R1 minus R2. So simply we can write force on 1 by 2, that is K Q1 Q2 upon magnitude R1 minus R2 cube into vector R1 minus R2. This is the vector form. Now suppose we think about force on Q2 by Q1. Then that will be in the direction from Q1 to Q2 because Q1 is repelling Q2. So that will be in the direction 1 to 2. So we can write force on 2 by 1, that is equal to K Q1 Q2 upon R21 square into R21 caret. R21 caret is the unit vector in the direction of this force. But from figure we can observe this thing, R21 caret and R12 caret both are in opposite direction. Both are unit vectors. So we can write R21 caret, that is minus R12 caret. So replace this R21 caret by minus R12 caret. So we can write minus K Q1 Q2 upon R12 square into R12 caret. Magnitude wise R21 and R12, that is one of the same thing. So resultantly we can write F21, that is minus K Q1 Q2 upon magnitude R1 minus R2 cube into vector R1 minus vector R2. So we can observe this thing. Say this one and this one are same except this negative sign. So we can write F21, that is minus F1 2. So if we take force on 1 by 2 or force on 2 by 1, or we say force between those two, after all that is one of the same thing. Magnitude wise it is same one, but just the directions are opposite. Clear? Now example 1.4. Coulomb's law for electrostatic force between 2 point charges and Newton's law for gravitation force between 2 stationary point masses. Both have inverse square dependence on the distance between the charges or masses. A. Compare the strength of these forces by determining the ratio of their magnitudes. 1. For an electron and a proton, and 2. For 2 protons. Then B. Estimate the acceleration of the electron and proton due to the electrical force of their mutual attraction when they are 1 angstrom, which is equal to 10 raised to minus 10 meter apart. Mass of proton, that is 1.67 into 10 raised to minus 27 kilogram, and mass of electron, that is 9.11 into 10 raised to minus 31 kilogram. Now see, charge on electron and proton, that is E equal to 1.6 into 10 raised to minus 19 coulomb. Mass of proton 1.67 10 raised to minus 27 kilogram. Mass of electron, that is 9.11 10 raised to minus 31 kilogram, given to you. Okay. Now, electric force between electron and proton. So charge of electron is minus E, charge of proton, that is E, and the force will be attractive force. So attractive force is represented with negative sign and repulsive force is represented by positive sign. So Fe, electric force, that is minus K E square upon R square. And now gravitational force between proton and electron, we can write minus G MEMP upon R square. Negative sign represents attraction. Now, suppose we take the ratio of these two forces, then electric force upon gravitational force, that is K E square upon R square divided by G MEMP upon R square cancelled. So you will get K E square upon G MEMP. Now in this equation, substitute the value of K, E, G, MEMP, and then after solve this one, you will get this particular ratio. તમે ગણજો value substitute કરીને બેટા. Then after, the ratio of electric force to gravitational force between two protons. So K E square upon R square, that is the electric force, divided by G. Now between two protons. So we have to take mass of protons. So MP into MP. So we can write G MP square upon R square. R square cancels. So again we will get K E square G MP square. Now here substitute value of K, E, G, MP, and then solve this one. You will get the answer. Now, electric force, that is K E square upon R square. K, that is 9 into 10 raised to 9. E 1.6 into 10 raised to minus 19 whole square. Then R, 1 angstrom separation is given, 1 angstrom, that is 10 raised to minus 10 meter. So 10 raised to minus 10 square, whatever is the answer now here. Now acceleration produced, we want to calculate, say, the acceleration of electron and proton due to electric force. So we have equation force F equal to ma, so acceleration equal to F upon m. Now if we want to calculate the acceleration produced in electron, so acceleration of electron, that is force on electron, that is electric force, so simply Fe upon mass of electron. Now substitute the value of Fe from this one here, calculated one, substitute it here. Mass of electron is given to you, then calculate, you will get acceleration of electron. Now to calculate acceleration of proton, we can write AP, that is electric force upon mass of proton. Electric force, substitute this particular calculated value of electric force here, and mass of proton is given to you here. Substitute these values, then solve it, you will get acceleration of proton. Clear? This is somewhat lengthy example. Now example number 1.5. A charged metallic sphere A is suspended by a nylon thread. Another charged metallic sphere B, held by an insulating handle, is brought close to A such that the distance between their center is 10 centimeter as shown in the figure A. The resulting repulsion of A is noted. For example, by shining a beam of light and measuring the deflection of its shadow on a screen. Spheres A and B are touched by uncharged spheres C and D respectively as shown in the figure B. C and D are then removed and B is brought closer to A to a distance of 5 cm between their centers as shown in the figure C. What is the expected repulsion of A on the basis of Coulomb's law? Spheres A and C and spheres B and D have identical sizes. Ignore the size of A and B in comparison to the separation between their centers. Very simple. Now see, suppose initially sphere A and sphere B are charged. Charge on A, that is Q1, charge on B, that is Q2, and these two are separated by distance 10 centimeter. Say this distance is R. Say this distance is R. So we can write the force between A and B, that is K Q1 Q2 upon R square. Now, if A is touched with identical sphere C, then charge distribution will take place here. And when A and C are identical one, charge will be distributed equally. So, charge on A will be Q1 by 2 and on C will be Q1 by 2. Similarly, if B is touched with identical sphere D, then charge on B will be Q2 by 2 and charge on D will be Q2 by 2. Now A and B are separated from C and D, and then A and B are placed at 5 centimeter from each other. Initially they were separated by 10 centimeter, now 5 centimeter. It implies that we can write R dash, this distance, that is R by 2, half of 10. So that is R by 2. Now new force F dash, that is K Q1 by 2 into Q2 by 2 divided by R by 2 whole square. So that is K Q1 Q2 by 4 divided by R square by 4. So 4 cancelled. Means resultantly we will get K Q1 Q2 upon R square, but that is the initial force. So we can say F dash equal to F. Clear? So that is your answer. Now next topic, that is forces between multiple charges. It implies that forces between more than two charges. Suppose we have assembly of more than two charges, then if we want to calculate the force acting on any one charge due to all other charges, then what we have to do? So simple method is this one. This is called superposition principle. If we want to calculate the force acting on any one charge due to n charges, then we have to take the vector summation of the forces acting on it due to each and every charge, and that is called superposition principle. Now see, suppose as shown in the figure, we have the charges Q1, Q2, Q3, Q4, and suppose the position vectors are as shown in the figure of Q1, that is R1, of Q2, that is R2, of Q3, that is R3, and of Q4, that is R4. Now suppose we want to find the resultant force acting on charge Q1 due to Q2, Q3 and Q4. So we have to calculate the charge acting on Q1 by Q2, then charge acting on Q1 by Q3, and force acting on Q1 by Q3, and then force acting on Q1 by Q4 using Coulomb's law. So force on 1 by 2, that is K Q1 Q2 upon R12 square into R12 caret. Or we can write K Q1 Q2 upon, now R12 caret, that is R12 upon R12 cube. We can write, because R caret, that is vector upon its magnitude. So we can replace it by R12 upon R12, resultantly here we will get R12 cube. So F12, that is equal to K Q1 Q2. This R12 cube, that is magnitude R1 minus R2 cube, and vector R12, that is as shown in this figure, that is R1 minus R2. Similarly, force on 1 by 3, that is K Q1 Q3 upon magnitude R1 minus R3 cube into vector R1 minus vector R3. Then force on 1 by 4, that is K Q1 Q4 upon magnitude R1 minus R4 cube into vector R1 minus R4. Now the resultant force on Q1, that is F1, that is the vector summation of all these forces. So that is force on 1 by 2 plus force on 1 by 3 plus force on 1 by 4. So F1, that is, now from these three equations we can take KQ1 common. So KQ1 into bracket Q2 into R1 minus R2 upon R1 minus R2 cube plus Q3 into R1 minus R3 upon magnitude R1 minus R3 cube plus Q4 into R1 minus R4 upon magnitude R1 minus R4 cube. So we can write KQ1, that is sigma I equal to 2 to 4 Qi into R1 minus Ri upon R1 minus Ri cube. Suppose in this way we have the assembly of n charges and we want to calculate the force acting on charge Q1, then we have to calculate the force acting on charge Q1 due to raised n minus 1 charges, and then after we have to take the vector summation of all those. So we can write force on 1 by n charges, that is KQ1 I equal to 2 to n Qi into R1 minus Ri upon magnitude R1 minus Ri cube. And this is also called superposition principle. Clear to all of you? Now example 1.6. Consider three charges Q1, Q2, Q3 each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge Q with the same sign as small q placed at the centroid of the triangle as shown in the figure? Now see here. This one is the equilateral triangle with side L. At this vertices A, B, and C, charge small q is placed. Say these charges are Q1, Q2, Q3, and all these are equal. Q, Q, Q. Then at the centroid, capital Q charge is placed. Now we want to find the resultant force acting on this capital Q charge. Now, as discussed in the previous theory, we have to calculate the force acting on this capital Q by the charge at A, then by charge at B, and then by charge at C. And then after we have to take the vector summation of all these. Now, centroid is at the equal distance from each vertex. Suppose that distance is R. So magnitude wise, the force on capital Q by A, by B, and by C, that is same one. Suppose we say force on capital Q by A, that is F1, by B means charge at B, that is F2, and by the charge at C, that is F3. Then magnitude F1 equal to magnitude F2 equal to magnitude F3. And that we can write K small q capital Q upon R square. And say this is F. Say this is F. Now R is how much? So we know this thing, the distance of the centroid from vertex, that is equal to L by root 3, well L that is the side of the triangle. And how that is L by root 3? So that is just written here. Actually no need to write this one. Simply you can take that distance R and keep it as it is. No need to introduce this L. Then also you will get the answer. Now resultant force of F2 and F3. So magnitude wise we can say magnitude F2 plus F3, that is under root F2 square plus F3 square plus 2 F2 F3 cos theta. But F2 and F3 both are equal to F. So we can write F square plus 2F into F, that is F square cos theta. But theta, that is now angle between F2 and F3, that is 120. Okay. From the figure we can understand, because all these forces are repulsive. So forces will be in the directions as shown in this figure. Now force 2, 3, resultant of 2 and 3, that is F square plus F square 2F square plus 2F square into cos 120, that is minus 1 by 2 raised to 1 by 2. So resultantly this will be equal to F. Now magnitude of F1, that is equal to magnitude of F2, 3, a resultant of 2 and 3. And in figure we can see this F1 and resultant of 2, 3. These two are in opposite direction. And therefore, F1 plus F2, 3, that is equal to 0. But F2, 3, that is F2 plus F3. So we can say the resultant force on the charge capital Q at the centroid, that is F1 plus F2 plus F3, and that is equal to 0. Clear? Now example 1.7. Consider the charges Q, Q and minus Q placed at the vertices of an equilateral triangle as shown in the figure. What is the force on each charge? Now see, at A, charge Q1, that is Q. At B, charge Q2, that is Q. And at C, charge Q3, that is minus Q. Now suppose first we calculate the force acting on Q1. Okay. Now see, charge Q1 is Q, positive charge. So due to charge at B, the force on it, that is repulsive one. But due to charge at C, which is negative, so the force on Q1 is attractive one. But magnitude wise, force on 1 by 2 and force on 1 by these 3, both are equal. So we can write that is K Q square upon L square. L, that is the side of the triangle. So that is the distance between two charges. And say that is F. Say that is F. So we can write now resultant force on F1, that is magnitude of F12 plus F13, that is equal to under root F12 square plus F13 square plus 2 F12 F13 cos theta. Now here from figure we can understand this thing, the angle between this F12 and F13, this angle that will be 120 because this inner angle that is 60. So these two forces are equal in magnitude and it is F. So we can write F square, 2F square. This one F, so 2F square cos 120. So this resultant will be F. So we can write in the vector form F1 that is K Q square upon R square into R1 caret, where R1 caret is the unit vector in the direction of this force F1 as shown in the figure. Similarly, now force on charge Q2. So due to Q1 repulsive, due to Q3 it is attractive. Now again, exactly like force on 1, we can write the force on 2 that is K Q square upon L square into R2 caret, but that R2 caret is in the direction of force F2 as shown in the figure at angle 60 degree with respect to this positive x-axis, we can say. Clear? Now force on Q3. Q3 is negative. So these two forces by 1 and by 2 will be attractive one. Both will be equal in magnitude. So force on 3 by 1 and force on 3 by 2. That is KQ square upon L square and say that is F. So resultant force on 3, that is magnitude wise, that is F32 plus F31 magnitude. So that is under root F31 square plus F32 square plus 2F31 F32 cos theta. So we can again write 2F square plus 2F square, but now the angle between F31 and F32, see here in the figure, that is 60, this angle. So cos 60. So we will get this resultant is root 3F, so that is root 3 KQ square upon L square. So in vector form F3, that is root 3 KQ square upon L square R3 caret, and R3 caret, that is the unit vector in the direction of resultant force on on Q3, and that is F3. So as shown in the figure, the direction of R3 caret will be there. So these are the forces on each charge. Clear?